Okay, so this is a continuation of my series of lectures on limit theorems. And it's a pretty heavy section, so that's why I'm having to split up all of these lectures into parts. Okay, so this is 3.2.3 theorem, part B. Okay, so if x converges to little x and z is a sequence of non-zero reals that converge to z, which is not equal to 0, then limit of xn over zn is equal to x over z. So the ratio of the limits. Okay, so before writing the proof, I just want to say recall that the triangle inequality implies the following corollary for any two real numbers. And then also, okay, so that was a corollary of the triangle inequality they were going to need in order to prove this theorem. Okay. Okay. Also, we're going to need results from the previous lectures. In particular, we're going to make use of the result that states that the limit of the product of two sequences is equal to the product of the limits. And that's how we're going to establish this equality here. Okay, so with that in mind, to get the proof started, we will first show the limit of 1 over Cn under these assumptions is equal to 1 over z. Okay, if we're able to establish this, then we can use that to prove this by applying what I just stated, that the limit of the product of sequences is equal to the product of the limits. So if that is equal to that, then 1 over zn times xn in limit will be equal to x over zn. So that's why we're doing this first. It just makes things a little bit simpler. Okay, so with this aim, so this goal, let's say alpha equal to the absolute value of z over 2. And so alpha is some positive real number. Okay. Now recall from our hypothesis over there that z is not 0, right? It's a non-zero real. So it could be negative, but we make it positive with the absolute value. well, we are dividing it by 2 for a reason we'll see in a bit. So that's definitely some positive real number. And we know that, okay, alpha is greater than 0. All right. We're also assuming that Zn converges to Z. And we know that alpha is some positive real number, so we can use the definition to get some bound on the distance between Zn and the limit according to that alpha. So I'll just write that, I guess. So since the limit of Zn is equal to Z, there is some index, say K1, so that the absolute value of Zn minus Z is at most alpha, right? It's just some positive real number whenever n is greater than that index, or greater than or equal to that index. And so that's just applying the definition of the limit. Okay. So this is going to imply, so I'll call this equation, this inequality here star, this corollary of the triangle inequality. This together with that, okay, imply that negative alpha is less than or equal to minus Zn minus C, which is at most absolute value of Zn minus absolute value of Z. Okay, so why is this the case? Well, let's say we know this is true, right? Okay, so if we multiply both sides of this by a -1, the inequality is going to flip and we'll get this, right? Negative alpha is less than or equal to negative of that, just by multiplying that, this inequality by a -1. I suppose like it won't matter, but there, whatever, right? Now, for this side here, we know, well, Zn minus Z is greater than or equal to Zn in absolute value minus absolute value of Z. Okay, so, or we could say Z minus absolute value of Zn, which implies if we multiply this by a -1, we get negative distance from Zn to Z is less than or equal to, the inequality flips, Zn and C. So that's where this, this inequality comes from. Okay, oh, I almost forgot. This is only going to be true whenever n is greater than or equal to K1. Okay, so this is true whenever that holds. Okay. So in particular, what is this going to imply? So this also implies that 1/2 of Z, which is equal to Z minus alpha, is less than or equal to the absolute value of Zn, again, when n is greater than or equal to K1. Okay, so why would this be the case? Okay, let me make sure that I've written this down correctly. Okay, so how do we work with this? Where is the definition of alpha? Where is it? So if we move this z over here, right? So if we add z, we get, I wish I had like sliding boards or something, but if we added the absolute value of z there and the absolute value of z there, we get that z minus alpha is at most the absolute value of zn. But z minus alpha, because of the way that we chose alpha, is that. Okay, so in particular, we have that the absolute value of z over 2 is at most the absolute value of zn, whenever n is greater than or equal to k. Okay, so we have this relation, this bound between the limit and zn. So if we divide both sides of this inequality by absolute value of zn, divide both sides by absolute value of z, and multiply both sides by 2, we get the following relation. So maybe hence 1 over the absolute value of zn is at most 2 over the absolute value of z, by doing that operation that I just mentioned. Oh, I have to always say this to keep track when n is greater than or equal to that index k1. Are we good right now? Am I moving too fast? Okay, well, again, I've paused to explain where these inequalities pop up. In the textbook, there is no explanation, so hopefully me breaking down each of the reasons here is helping a little bit. Okay, so our goal, if we look back to the first sentence here, is to show this, that the limit of that is at most that, or no, not at most, the limit of this sequence is equal to this. So let's look at this in absolute value. Next, observe that the absolute value of 1 over Zn minus 1 over Z. Let's just combine my terms here. So what is this? This is going to be Z minus Zn over Cn times Z, right? Just combining those fractions. Okay. Now, we can write this as a product of absolute values. So Zn Z times the absolute value of Z and Cn. Okay. Okay. So we know that, so this inequality here is important. 1 over the absolute value of Zn is at most 2 over the absolute value of Z. So maybe I can like write one more equation here.
Professor?
Yeah.
Why is Z minus Zn equal to 1?
Not equal to 1. So
Oh, never mind. You moved it. Oh, okay. Okay, I see.
yeah, so it's like maybe without erasing too much. Does that help?
Yes, thank you.
No, it's okay. These things are really like, there's like lots of little subtle things that are happening right now. But now we're here, right? But this is like saying that times that times that, right? Because you can always split the absolute value up into a product. But the absolute value of the product is the same thing as the product of the absolute value, so that's all we've been doing here. But now we can get a bound because we know that is at most that. So if we replace that by 2 over the absolute value of Z times that, we get 2 over absolute value of Z squared times Z minus the sequence. Again, we should have in the back of our mind here that n is greater than or equal to K1 for this inequality to hold. Okay. So now we're in luck. We know that for large enough n, this thing is as small as we want, right? The distance between the limit and the sequence can be as small as we want for large enough n, right? So we can make it small enough to where it gets rid of this term here, and if there's just like an epsilon. So what would that be? It would be so this isn't a part of the proof yet, but I'm just like going to take a guess. So we want that to be 2 over limit squared. We want this, if this is less than, what is it? Absolute value of Z squared over 2 times epsilon, then that'd be equal to epsilon. So we want that to be strictly less than this number for some choice of epsilon. If we do that, then that is at most epsilon. And this, because we know the sequence converges to that limit, we can make that as small as we want. So I can say, so again, like maybe since the limit of Zn is equal to Z, if epsilon is greater than 0, there is some index called K2, so that the absolute value of Z minus Zn, the distance between these two things, it doesn't matter the order, it's just a distance, is less than the Z squared over, this is the thing we wanted, 2 times epsilon when n is greater than or equal to K2. So in red here is what we wanted. We wanted this to be small enough so that this is less than epsilon. So if that's smaller than this quantity, then that times that is at most epsilon. So now we just need to make sure that using this inequality here and using this inequality here happen at the same time. So in order to ensure that, we can say take k equal to the suit of k1 and k2. So k is the maximum of this index and that index, which means that if n is greater than that and that, then this inequality holds and this inequality holds, which means that that is at most epsilon. And observe one over Cn minus 1 over C is at most epsilon when n is greater than or equal to k. Hence, limits of 1 over Zn is equal to 1 over Z. So we've shown that, okay? Now, I ran out of room, but this is basically it. Because, why does that finish the proof of this result? Like I said at the very beginning, we know if you have two convergent sequences, our previous lecture, right? So to prove this, just say, so this implies the limit of xn times 1 over dn is equal to x times the limit of this. Which establishes the claim. Okay, this one was tricky because of all of the algebra involving the inequalities. But again, the way that you should learn these proofs is to watch my explanation a few times, write out the proof with me, and then put away your notes and try to recreate the proof on your own, justifying each step. That's how you will learn these things. Well, that's at least like how I learned. Okay. So that finishes the theorem 3.2.3, which had to deal with the basic algebraic properties of limits. So looking at sums, differences, products, quotients, taking limits of these types of sequences. Taking limits of sequences under these properties, I mean. So I'm going to go ahead and stop the recording there so I can make this its own video.